Hey, welcome back, class. This video, let's take a look at a concept. I'm calling it electron density and polarity. We could go by there. There's going to be multiple things talked about. This is just a little shorthand idea I have for this. So, one way, shape, or form, this concept is at the heart of what's happening with Lewis structures. So in previous lessons, we've talked about Lewis structures and just figuring out, based on the number of valence electrons, how different types of atoms pair together, whether or not we get single, double, or triple bonding patterns, right? And then lone pairs will be distributed in some way, shape, or form, because remember, all these electrons are negative and they're pushing on each other, right? And then there's this constant attractive pull based on you've got the nucleus, and that's kind of at the heart of all of this, is this push and pull that's going on between the positive and negative parts of atoms. So let's just jump in and take a look at this idea that we have, like electron density and polarity. We use this to really try to help us visualize in our mind's eye kind of what's happening with atoms and molecules and even ions as well. So let's just take a look and jump in here. So electron density. So when we talk about density, remember, density is just how much stuff is in a certain amount of space, volume, right? So gotta go to the coffee. So with that said, let's take hydrogen, for instance, right? So in our molecule kits, this represents hydrogen. Remember, white is the universal color for a hydrogen atom. And then, of course, we have our single bond right here. Remember, hydrogen, right? Each of these hydrogens, you remember, hydrogen brings in one valence electron, right? So hydrogen, it brings in one valence electron. And so that's this one here. This other one right here is bringing in another valence electron. And what we typically do is we say, wow, right there, that's where that covalent bond is occurring, right? So where that sharing of electrons is occurring is right there in that region of space. So they're not physically touching. I mean, they get really close, but they don't actually touch. If we were to keep going down and further and further and further into the space, we realize that there's still space in between there, even though to our limited vision and the way we see things, it looks like they're touching, but they're really, really not, right? Because there is this negative particles, they are pushing away from each other, right? There's only so far matter can be compressed together before it's going to push away. It's just a natural property. So we have seen that we then go so far as to just draw a little line there, and we call that line that bonding pair. That's our covalent bond, right? And then electron, a dot notation, we tend to draw something like this, just to show those pair of electrons being shared in that same space. So we have all of these, right? And then, of course, remember, there's a proton one, there's no neutrons. Remember, we've got our nucleus, right? And then you've got that one orbital that's going around there, and then there's that one electron that's orbiting on that first orbital, at the first energy level, hydrogen atom, right? So all these models represent that. What we're going to do is now take a look at this from a little bit different sort of concept, one that sort of expands out, maybe something that's happening a little more real time, right? So at the heart of the hydrogen atom is a positive nucleus, right? There's that one proton. Essentially a proton, like a proton ion, or a hydrogen ion really is a proton, if you think about it. It doesn't have that electron. Now, if we have an electron, then what we're saying is I'm going to take, we're just going to look at just one of these hydrogens all by itself. If I'm looking at just that one hydrogen, then at any point in time, that one electron, it could be in this region of space. It could be here. It could be here, 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 here. It could be anywhere at any point in time. If I were to freeze time and say, and take a look at where that electron is. It could be in any of those spaces, right? Let's think about this. If that's true, then that means that electron could be there, or it could be there, or there, or there. It could be in any of these spaces. So let me do this to try to make them all even. Each time I put a dot, what I'm doing is I am saying that electron could be in any of these spaces at any point in time. There's not that many electrons. We're just a concept that the electrons could be occupying that space at any moment in time. Well, let's think about this. We've got, let's see, let's copy it. So let's think about this. Here's our hydrogen molecule. Think about it. Right there, this represents a bond. This region of space right here is where we're saying that this region of space and this region of space we're saying is the same. That region of space is being shared. We say our covalent bonds represents a sharing of electrons. And so in this example here, we can see that the density, what we have here, this density diagram, this density model, is representing the concept of the space that this atom is taking up based on how densely populated the electrons are around it. And we're particularly focusing on the valence electrons because those are the ones that are interacting back and forth between bonding and chemical reactions and stuff like that, right, primarily. And then there are other examples where you have things that shift up and down and move from being in a covalent or in the outer valence region to where the non-valence region shifting back and forth, and that's all part of chemistry as well. That goes particularly like with transition metals and stuff like that, right? Right now we're just focusing on these. We're focusing on this concept of covalent bonding in that space, in that covalent orbital, right? Covalent orbital, there's co-together valent shell. All right? So that's that. But, and if you look at this, I keep doing that, sorry. If you look at this, right now, this model here, we build these models based off of mathematical models that we've been doing with research for years. When I say we, I mean scientists who invest their life and time into this. And we should thank them. That's the reason why we have all these modern conveniences that we have. If you take a look at this, that looks like things are fairly evenly distributed. And we would say that it has a certain look, a certain even distribution pattern. We might say that it has some symmetry to it, and that's going to come into play here real soon. So let's take a look at two other examples, and let's expand this concept out just a little bit further. All right. So let me go ahead and clear our board here. Let's take a look at hydrofluoric acid. So we've got hydrofluoric acid. So again, there's the hydrogen. And then here is our fluorine atom, right? So hydrofluoric acid. And then, of course, there's our covalent bond. If we were to look at the Lewis structure for this, we know that fluorine, remember, brings in already 7 valence electrons, right? So hydrogen already has 1. The fluorine already has those right there, right? Those 2, 4, 6, 7. And so there's covalent bonding that occurs right there. So that's how I got that, right? Definitely get that over there. So now let's think about this. If we go back to our periodic table and we look at fluorine, right? Fluorine over here in the second period. So we've got 1. So there's 1, 2 orbitals, and the 7 valence electrons are in that second orbital, so we can envision, kind of the way this is modeled, that the valence electrons are further away from the nucleus. It's a relatively larger radius of space in which those electrons are orbiting and moving all over the place. But remember, those electrons can be here, 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 here. They can be at any point in time. I got to figure out a way to turn these things off. At any point in time, those 7 valence electrons can be anywhere around that fluorine atom. And of course, they're all negative particles. So, I mean, this is not magnetic, but we can take what we know from our elementary school days. That if something were, if you had 7 magnets close together and they were all the negative sides were close together, that they would repel each other, they would push away. They would only be so close they could get. They're going to push away into some amount of evenly distributed space. Same thing is happening here. All right. So if we go back to this, then what we have is, once again, we have, oh, I already have that color there. I'm good to go. So we have our positive nuclear core for the hydrogen. And remember, we said at any point in time, that hydrogen atom could be here, right? Or the hydrogen electron could be at any of those spaces. And remember, we said we had a second one of those, so to save some time, I'm just going to go in here and copy it, and then I'll paste it. And then remember, we said that could happen right there, right? However, this time, we've got a fluorine atom where there's a second orbital. So there's 7 valence electrons, and so those 7 valence electrons at any point in time could be anywhere around that second orbital. I'm going to be here a while. It's always fun when I'm doing this in class because you can always hear people, their pencils tapping the paper. I can hear the tap on their desk and through their notebook onto the desk. It's kind of funny. As long as I keep tapping, students tap on their paper. It's kind of neat. It's kind of fun. So you should be able to visualize that makes sense. This fluorine is taking up more space. Well, what we need to realize is that the positive part of each of these nuclei are pulling and attracting each other. This hydrogen is pulling the fluorine towards itself, right? And the fluorine is also pulling the hydrogen towards it. The fluorine is pulling it towards itself, right? There's this constant pushing and pulling. Now, when they get too close, the electrons, they push and help maintain that space, right? All right, this is a very loose interpretation of what's going on. So that means these atoms are attracted to each other, and we can see right there, that region of space is the same as that. But we can see through this electron density model, what we can see now is that there is what looks like some asymmetry to it. If you look at it, the electrons are not evenly distributed around the entire molecule. So that has an effect on how the molecule works. If you think about it, so once again, we've already said that there is asymmetry to this. So it is asymmetrical. So now we're going to look at this concept of electronegativity. All right, we're going to look at what we call electronegativity. So electronegativity, all these atoms are essentially have some electronegative value because of the electrons around there and because of their electron density, right? based on their radius, how many electrons are there, all that stuff. All these properties kind of play together to give atoms these different properties. Some atoms hold onto those electrons more tightly. Some of them hold onto it more loosely. If you were talking about electricity, where those types of atoms are very good conductors. We tend to see that, for instance, in metals, right? Those electrons easily come off of there, and that flow of electrons is energy. If we harness the energy together, we get all this electricity. It keeps shutting off of that motion sensor. Anyway, I digress. So, electronegativity. There is this thing called a Pauling scale. It's a really smart dude. 2 Nobel Prizes, chemistry, really smart guy. Because of these concepts and his research that he invested, it's a lot of reasons why we have a lot of modern amenities with our medicines and technologies that we have in industry, and the way we can build stuff more efficiently in greater productivity. It's wonderful stuff here. We're going to find this plays a part in everything we do. You'll notice that there's numbers here. So all these numbers are an electronegative value, but we're basically just looking at like an absolute value of it. The larger the number, the greater the electronegative value it has, and we're going to interpret that as the greater pull that that atom has to pull other atoms towards it. And so what we have to envision is this constant tug of war. So there are 2 atoms, and they're constantly pulling towards each other back and forth. And as they're pulling, there's this constant moving back and forth. The atoms are moving back and forth. They're in motion. Remember the whole kinetic theory of motion. They're constantly moving. Constantly, no matter what. What we're doing is taking a look at what is the overall effect of the movement from all these electrons interacting back and forth and pulling and pushing on each other, right? From atoms pushing and pulling on each other. So let's go in and take a look. So we're doing hydrofluoric acid. So we need hydrogen, which has a value of 2.1. All right, and fluorine has a value of 4.0. All right. So let's go back and let's use that. Let me get rid of that for you. So hydrogen, we said, had a value of 2.1, and fluorine has a value of 4.0. Let me write this up here just a little bit more. This is going to make sense why I'm going to do this here in just a second. So what we can see is there's 2.1 of energy, so to speak, being pulled in that direction due to the electronegative value that has already been calculated through research, and 4.0 by the fluorine in this direction. So as a tug of war, if you had an overall effect of 4 in that direction and 2.1 this direction, the net effect is that everything shifts in the direction of the 4.0, but not with all of it. So there is an overall effect in that direction. Now we're talking about electron shifting, which means that this side now has relatively less electrons, so it technically is more positive. And that's where we come up with the idea of positivity, right? The difference between these two numbers is 1.9. It's 1.9. So we go back to this right here, and if we take a look, anything that is 2.0 or greater is an ionic bond. There's no ionic bonding happening here, and with any of these molecules that we're going to look at this level of study, we're going to be looking at only just covalent or only just ionic. So all of these that we're looking at right now are covalent. What I need you to see is that there is wiggle room. It says between 0.3 and 1.7, but what about 1.8 and 1.9? Well, what we do is we come over here and we take a look, and we see that due to the asymmetry of this molecule, that there's an overall effect of this being a polar molecule. Because due to the asymmetry, we see that there is more electrons on one side of the molecule compared to the other. So we would say that this side of the molecule here is partially negative, and we would say this side is partially positive. So what that means is there's an overall net pull through that molecule. So now what we do is we come down and draw the same thing parallel to it. Remember, your math teacher said you can move arrows and things like this, rays up and down parallel to each other, and then they still have the same value, right? So here's our partially negative, partially positive side. The electronegativity difference is 1.9. We would say this thing has asymmetry. It's an asymmetrical molecule. It's a polar molecule, all right? And as a result of this hydrofluoric acid being a polar molecule, the electronegativity difference 1.9, we're good to go. We would say this is a polar molecule. It's pretty good, right? That makes sense. Now we have a visual, and you need to try to see all your molecules in this sense right here. Everything we've been doing, we've just been chipping away at bits and pieces of how all these things interact, right? All right, so let's go take a look at another one. I'm going to go over here first, make sure this light doesn't turn off. I'll be back, and then we'll take a look at another molecule, all right? Take a look at oxygen. Let's take a look at an oxygen molecule. We've done this, we've built this in the past, right? O2, we know that it's double bonded, and we have those 2 lone pairs on each, so we have to visualize that there's 2 lone pairs in this region here, and then 2 lone pairs in this region here, and it's causing the molecule to sort of bend on 2 sides, and we end up getting this double bonding that occurs, right? And notice those double bonds, the atoms are actually closer together than they would be if they were single bonded, right? So what's the effect on this? Well, let's take a look at it. Let's go back to our periodic table. Let me erase this from before. Usually I try to clear that whenever I leave the page, but so we can see oxygen, right? And then oxygen, there it is, group 2, just like fluorine. So it has 6 valence electrons each, O2, so we need 12 valence electrons all together, correct? So this fits, 2, 4, 6, 8, 10, 12. There's 8 octet rule satisfied, we're good to go. Well, once again, we know we have that positive nuclear core, and then come back here. Remember, in the first orbital, those 2 electrons could be anywhere around there. We have a second orbital with 6, so that's taking up a relatively larger volume of space. This is actually called stippling. And so if you've ever seen pictures where it looks like there's a bunch of dots, usually you'll see it in old black and white type pictures, sketchbooks. Lots of people still. I don't know if lots of people still do it or not. It was very popular for a long period of time. You take a very fine point pen with ink and you use dots to essentially create this mosaic that is. You can make some beautiful artwork with it. Stippling it, it's really fun. You should try it. So now, O2, we need 2 of these. So I'm going to copy that. I'm going to paste it. And so we know that we have something like this. We can already see that there is what looks like asymmetry around it. The molecule is pretty even. The electron density, the electrons are pretty evenly distributed around that molecule. All right. And so we kind of already think, I think I know what's going to happen with this one. Let's just play this out and see. So Oxygen, we go back and we see electronegativity value for oxygen is 3.5. So we're going to come back here. I'm going to put 3.5 and I'm going to put 3.5. So that means there's a pull of 3.5 in this direction, and there's also a pull of 3.5 in that direction. So if you remember your basic number line, if you have 3.5 in this direction and 3.5 in that direction, effectively you have zero difference. So there is zero difference here whatsoever. All right? So since there's zero difference, we actually say that there is no net dipole. So what we mean by that is this. There are not two sides, to pole means end or side. There are not two sides of this molecule that are unevenly distributed with electrons. In our previous example, where we had hydrofluoric acid, we did have an uneven distribution. And so when we drew out the hydrofluoric acid before, so let me do this. What I can do is I can recreate hydrofluoric acid for you. Copy. Paste. I can recreate it for you by simply removing that outer layer, that second orbital, and all of a sudden now you should see, hey, that looked more like the hydrogen. And remember, we had done this. We said that there was this pull going through it, and then we did this, and we said this side was more partially negative and partially positive. That's what that symbol sigma means, is partial, right? Based on electronegativity values. So this part right here, that is what we call a net dipole. There were two sides of the molecule unevenly distributed with electrons. And so here there's no net dipole. So we say that this has symmetry. It is symmetrical. As a result of that, since there's not one side more charged with electrons than the other, then there's not a polar side. We just say that this is a non-polar molecule. And that's it. Just like we said that this one right here was a polar molecule for the opposite reason. So now you know what these weird looking arrows mean. I didn't tell you in the previous part because I wanted to wait till we got to here, go back and reflect on it so you could then see them both side by side, right? Well, that was what I was wanting anyway. This part right here, where we said there was a pull from here to here on this, we call this a dipole moment. At that moment in time, as those atoms come close together, then there is two sides that are unevenly distributed in electrons. And so there's a moment in time where things shift towards one side, a pole, and we get a positive and negative difference. And that constant movement back and forth is what creates this polar or non-polar property that we see in all these different molecules. And so that's what we're doing with our Lewis structures from here on out. Just trying to get that all figured out. So, take this, make sure you've got some notes, rewind the video, make good notes in your notebook, draw all this stuff out, and if you have to draw it multiple times, by all means do so. And work on those problem sets that I've provided for you, and of course, as always, I provide the answers to that, and then you can always reach out to me if you have any questions. I'm always happy to help. That's what I'm here for. So, glad you were here. Always great learning with you. If you haven't invested in a molecule kit yet, I highly suggest you do. I mean, they're just toys. When we're kids, we put things together. Our brains are naturally intuitive. We want to kind of touch things and move things around and see patterns. The more you do it, the easier it becomes, and the easier all these things begin to make sense. So have fun with your problem sets. I will see you in another lesson really, really soon. Take care, and go get yourself some coffee. It does wonders for thinking and stuff like that. Bye. I'm going to go do some more work.